fundamental theorem of calculus has two parts. The second part is used way more than the first part, but the first part is essential for being able to do the second part. So we'll start with part one. So we've already defined that the integral from a to b is the area under that curve, and we've been measuring it so far with rectangles. Okay? What we're going to do now is we're going to say, I've got some curve, it starts at A, but we don't know where it ends. It ends at some value of x. And I call that I of x, integral from A to x, and then we introduce t as another variable, but it really doesn't, it's sometimes called the dummy variable because you don't really need it. The main variable is the variable x. So now we're trying to figure out the area under the curve starting at A and going up to some variable x. And since that x is changing, we should be able to get an equation for this value. We have the following properties. Okay? Our function has to be continuous and differentiable from A to B. And the following weird result happens, is that if you took the derivative of I to the x, in other words, the derivative of this integral function of all the areas from A to x, it always just equals f of x. And the other weird thing about this is it doesn't matter where A starts. If you went from 2 to x, it equals f of x. If you started at 5 and went to x, it equals f of x. It equals f of x every single time. And I found a really good video that shows how the Riemann sums and all of this fits together with your definition of the derivative. So we're going to watch that right now.
So far in calculus, we've seen a bunch of different named theorems. The intermediate value theorem, the extremum value theorem, the mean value theorem, but in this particular video, we're going to talk about the fundamental theorem of calculus. And in fact, it's actually two parts. This one's going to be part one, and there's a second fundamental theorem of calculus. That's going to be in the next video. Now, if we're going to call it the fundamental theorem of calculus, it better be a pretty big idea. And indeed, this is. When we talk about the fundamental theorem of calculus, the large picture is that there is derivatives and there is integrals, two different important components within calculus. Indeed, if we talk about the derivative, we're talking about things like the slope of a tangent line at a point. Well, if we're talking about a definite integral, we're talking about like an area underneath of a curve. These are two very different geometric concepts. And what the fundamental theorem of calculus does is basically take these two different ideas and find a way to relate them, to kind of mash them together. This definite integral, the integral from A to B of f of t dt, this is going to represent geometrically the area under the curve, the area above this particular interval, a, b. Now, this is a static thing. This is a number. If you gave me an a and a b, you would compute this and it would be some value like 7. But what if instead of a to b, I make a slight change and I say that now it's the integral from a up to x. And indeed, I'm now going to call it something. I'm going to call it a function g of x, because indeed, this is a function of x. Think of it this way. For every value of x, you get a different number out. A is some fixed thing, like say 3, and then you could ask 3 up to any other value of x. To help visualize why this is such a dynamic thing, imagine I take this particular x that we have here, and what if I move it? For every value of x, you get a different curve, a different region you're considering, and you get a different answer out for what that area is. G is a function of x. One thing to note here is that in this particular curve, I managed to draw one which is a positive function. This function of x is over the x-axis. So as I go to the right, as x is increasing, the area is also increasing. So this g of x here is an increasing function as long as f is positive. If in a different graph the function dipped beneath the x-axis and was negative at some point, then the g of x, the accumulation function, would start decreasing at that point as I was adding negative areas, contributions from beneath the x-axis.
Just going to pause it there. One of the things he said there that we're going to be getting to is this idea of accumulation. As the x moves, more area is getting added. So they use the word accumulation because you're increasing, or if part of it was below the x-axis, decreasing. So now we had our definite integral, which was area from a to b. Now that we introduce the variable x and have it change, we get a function.
Now, one point I want to make clear is that in this accumulation function, there's an a, there's an x, and there's a t. But they have slightly different philosophical meanings. When I look at the a, for example, a is just some fixed number like the number 3. And I'm saying that all of these intervals, for every value of x, I'm going from, say, 3 out to wherever my x would be. So a is thought of as a constant, a fixed value. The x here, that is the variable in my function of x. G is a function of x, and for every value of x, you get a number. So then, what's the t? Well, the t is a bit of a dummy variable. This is the variable when you're actually doing this integration. You think of breaking it up as a limit of sums by the definition. You'd have a t there. That's the thing you do to actually compute the area. And so, for every value of x, you'll use the t's to be able to compute what that integral is going to be between a and between x. Now, what is the fundamental theorem of calculus concerning? I told you it makes derivatives and integrals together. Well, what it's going to ask is this. Can I take the derivative of this g of x? G of x is a function. It depends on x. Derivatives takes functions to some other function. Why don't I try to compute the g prime of x? So let's ignore our picture for a moment and try to do that. Let's try to go and look at what the derivative of g of x is, and I will remind you that the definition of the derivative, when back in the day when we actually defined it, the definition of the derivative was the limit, as h goes to 0, of g of x plus h minus g of x all divided by h. That is my formal definition of the derivative. Okay, so let's do that. Well, g of x plus h and g of x, those are both defined in terms of these funky accumulation functions. So if I replace those, what I have instead is going to be the limit as a goes to x plus h. That's taking g and plugging x plus h in. A up to x plus h of my f of t dt. And then I subtract off g of x, so I subtract off the integral from a up to x of f of t dt. So this is what my limit does to this g function when the g is the accumulation function, the integral from a up to x of f of t dt. So now let's go back geometrically. Let's just look at the numerator of this difference of these two accumulation functions. Let's try to understand what that is. Because if I go here and write that, so this is the same numerator here, how can I visualize this? Currently, I've graphed the integral from a up to x. But let me overlay a to x plus h. It's going to look a little bit like this. That is, it's an integral from a all the way up to x plus h. And if I think of x plus h is slightly bigger than x when h is greater than 0. So now I want to do the difference between the two things. So the red is going up to the x plus h, the yellow is going up to x, and then their difference, so it's the big area minus the small one, their difference is just going to be this little red strip here. And I combine that. This little red strip is the integral from x up to x plus h of f of t dt. Now, this integral is the area under the curve, so can I approximate what this little red area actually is? I think so. Indeed, if you look at the width, going from x to x plus h, this width is indeed just h. Now, this little red strip is not quite a rectangle. Maybe on the bottom it looks like a rectangle, but it's some weird curve along the top. However, imagine that my h was really, really small, so my x and my x plus h were right beside each other. Well, you could approximate this as a rectangle with a fixed height. That is, we could say that this was the rectangle that had the width h, but had a height of about f of x. And you might say, well, hold on, no, it's it's not quite a rectangle. But as my h goes to 0, this is approximately a rectangle of width h and of height f of x. Let's take this result and let's put it back into my definition of the derivative, the definition for g prime of x. So this is where I was at earlier. I had my g prime and my definition of the derivative. I plugged in my accumulation functions, but now I can do something with that numerator. I know what that is. My approximation was that that numerator was just going to be the same thing as the integral from x up to x plus h of f of t dt, and that was approximately just going to be f of x times h.
And that's crazy. So, to recap, I really liked his pictures. We defined g of x as that area from a to x. We took the derivative of g of x and actually used your definition that you haven't done for a long time, not since your limits unit. Remember, the limit is f of x plus h minus f of x all over h. Okay? But g of x plus h and g of x, he had a really nice picture of showing those are both those area things. And the only difference would be the area from x to x plus h when you subtract them. And as h goes close to 0, your rectangle becomes as a width of tiny h and a height of f of x. As you go really, really small, it's going to be like a paper-thin rectangle. And then these h's cancel out beautifully. And you just have the limit as h goes to 0 of f of x, which has no h's in it whatsoever. So it's going to just be f of x. And this is connecting your integrals and derivatives together.
And then I'm just about done with my proof here because I got an h on the top, I got an h on the bottom. I can cancel those, and that just leaves me with f of x. So the grand statement of the fundamental theorem of calculus number 1 is that the derivative with respect to x, the g prime here, the derivative with respect to x of the accumulation function, the integral from a up to x of f of t dt is just f of x. And doesn't it sort of look here like derivatives and integrals cancel them? Indeed, we've got a derivative and an integral, and it does cancel. Now we have to be a little bit precise about what we mean by that. What we mean is exactly this statement. Note, by the way, that the t, that dummy variable that we have here, it becomes an f of x at the end. So this is a function of x. So the final answer should be f of x. It shouldn't be f of t, the dummy variable. And also note that this is very precisely needing to be written, the derivative not just of any integral, but precisely the derivative of the integral from a value up to x of some particular integrand in terms of t. So that is the fundamental theorem of calculus. It does have an assumption. It has that this original function f needs to be continuous on a up to b, where x is some value in between a and b. But there you have it. Finally, let's go and...
No, we'll do some questions ourselves and figure out things. But we have this huge result that's actually really simple. And the idea that... Here's our notes. The idea that the derivative undoes the integral, and we learned anti-differentiation at the beginning, saying that they were opposites of each other, but now it's getting connected to the areas. And so, as long as it goes from a to x, and a can be any number, this would be the same result if you started from 2 to x, 7 to x, negative 5 million to x. It's always f of x. So the a value doesn't matter. However, this x is important. So let's go to some examples. If that top value is just an x, life is really easy. Because our answer is just f of x. So if our function was 5 square root of 2t minus 1, and that dummy variable t is there, well then, when you evaluate all of that, it just becomes f of x. So you just replace the t with an x. We could probably do 1,000 of these in a row and you would be very good at them. Because if the format is in this way, where you're taking the derivative of the integral of something up to x, then everything straightforward. It is just f of x by the fundamental theorem of calculus, part 1. So we have to recognize the format. The format of this is, it's the derivative of an integral. And it has to go from a number up to x. Then we have a dummy variable inside. Does this match up with the fundamental theorem of calculus part 1? Yes, it does. So that means we can just replace those t's with x's, and we can say this is equal to sine of x over x minus 3. Good. Now part C is where things get a little bit interesting. It doesn't match up. It doesn't match up that we go just up to x. Can we just replace it with x squared plus 1 then? No, not quite. So what we're going to do is we're going to do a little substitution. If it was nicely up to just a single letter here, we could do the fundamental theorem of calculus. So what we do is we're going to make u equal to x squared plus 1. Then du dx, the derivative of that, happens to be 2x. So then you could write d du of this. Do you see how I replaced the x with the u? Okay. Do you see that we also replaced the dx with the du so that these matched up? However, we didn't have a du out in front before. We had a dx out in front before. Well, if I want this dx on the bottom, I want to use, I feel like blue. See how there's a dx on the bottom? That still needs to be there. So I'm putting a dx on the bottom there. You see how I added a du on the bottom that wasn't there before? Technically, I would like, I'm just put a little dotted red line through it. You see that those technically would cancel out if these were acting like fractions, and I know integrals aren't exactly fractions. However, they seem to follow fraction rules quite nicely. So what we have is that if I want d du of this, so it matches up perfectly with my fundamental theorem of calculus part 1, well, I would need to multiply by the du dx. It's kind of like a chain rule, so that the du's would cancel. My dx was on the bottom before. Now this new statement matches up to the statement that I had before. This part is now perfectly the fundamental theorem of calculus part 1. So that just becomes 3u eu. And then afterwards, I still have the du dx. But our original question was in terms of x's, not in terms of u's. So we did a little substitution to make the math doable. And now that we've done that, we can substitute back. The u was x squared plus 1. But now we have to also multiply by a 2x in the end. I mean, you could simplify this. I would leave my answer like this. I really like its format, but if you did want to combine things, you could. So as soon as that top number is not just a regular x that fits the fundamental theorem of calculus, we have this strategy a little bit of substitution, and the chain rule, which helps us solve for it. So sort of a rule of thumb. If that top number isn't just a regular x or a regular u or a regular variable, fundamental theorem of calculus isn't set up correctly. What we need to do is we need to do a small substitution in order to get it matched up. So try this next one on your own first, and I'll put up the answer and describe it in a second. And I gave you a little bit of a hint with this. If the area under the curve from A to B is one thing, if you switch the order of it, it's the negative. Put all of this together. So the first thing, I want the x up at the top. So I use this property that if you switch these two numbers, it's the negative. But my top number isn't just an x. Oh, I'm getting a little dt here. So I'm going to need to do a substitution. I'll let u equal the x cubed. And then my derivative of this du dx would be 3x squared. So I plug those values in. I want to get my fundamental theorem of calculus part 1 set up, so I need d du if I'm going up to u, which means I need to add the chain rule to du dx so that I still have a dx on the bottom, and my du, which I introduced on the bottom, sort of cancels out with the du on the top. Now, the green box is your fundamental theorem of calculus part 1, so we can just replace that t with a u. And then we substitute afterwards. Now, the fundamental theorem of calculus part 1, which connects the derivatives and integrals to kind of canceling each other out, leads up to the fundamental theorem of calculus part 2. And this is the part that gets used all the time. Part 1 is very rare. You might get a couple of questions on your exam that get you to look at it, and you have this, they'll probably put one with a not X at the top to see if you really understand it. But it's used quite, not very much. Remember doing lots with the fundamental theorem of calculus part 1? No.
I remember this.
But you remember this, the fundamental theorem of calculus part 2. This gets used a lot. Now I found a nice video that has 3 proofs online, but I don't think we're going to really look at it in depth. Trying to think of a really nice way of showing why we need the fundamental theorem of calculus part 1, but a beautiful result and a really simple result happens. Okay? So when we integrate, we've now made this connection with that definition of the derivative that the integral and derivatives kind of undo each other. So if they have to undo each other, well then integrating f of x becomes capital F of x, which is our antiderivative. And the beautiful thing that happens is if you want to find the area under the curve, and I cheated and showed you this already when we were doing some of our rectangles, that all you need to do is find your antiderivative. And then it's just as simple as plugging in b and subtracting, plugging in a. And we just have two values that we have to subtract, and that accounts for all the million rectangles in between that we were adding up with sums before. And it is really beautiful. I'll post on Teams a video I found with 3 different proofs of why this is true. They might be the kind of thing, maybe I should post this other video we watched today too. They're the kind of videos that sometimes you have to watch like 2 or 3 or 4 times to really like, okay, do I get this yet? Do I see what's happening here? So you might want to watch them more than once. But it's this simple, that it's just f of b minus f of a. And because it's that simple, people have provided proofs online because it's almost too good to be true that something so complicated, like the area under any curve, can be solved this simply. Okay. So we've got our steps here, how we're going to do it. We are going to have a definite integral like this. The fundamental theorem of calculus part 2 says you're going to rewrite and work backwards and write the antiderivative inside of big square brackets and still put the parameters a and b there. Then you're going to plug in b and subtract, plug in a. And we get, you're going to be so mad at me for making you do Riemann sums, because this is so simple as a result. But it all came from that idea of thinking of those sums. Fundamental Theorem of Calculus Part 1 puts it together, and there's some instructions for how to do it on our calculator as well. So, here we go. The scary thing is you're going to forget how to do all those Riemann sums. And you can't completely forget how to do them. So you still have to know how to do those Riemann sums, adding up those rectangles, thinking of a, like, here you would have an interval width of 3. So depending on how many rectangles you want to break it up into, you could do your left Riemann sums, your right Riemann sums. Here's a picture of what's happening here. I have my 3 over x graph, and I want to find the area under the curve from 2 to 5. That obviously isn't a nice, smooth, straight line, so we have no formulas for this. But now, if we integrate, right, I notice the 1 over x, that's my natural log. Okay, I could put absolute values here, but they're not necessarily, because our values that we're going to be plugging in are positive anyways. So we write our antiderivative in those square brackets, keep the parameter from 2 to 5 the same, and now you plug in 5, you plug in 2. We can write that as a decimal if we like. And we've calculated a very difficult area very quickly. Just going to show you on your calculator so you can see it as well. So without a calculator, this is what you would have as your final answer. If you had your calculator, I can go to y equals, I can type my function in, 3 divided by x. I can hit graph and I can see what it looks like. And then anything you want to calculate on your graph is your second trace button, second calculate. And now we see number 7, our integral is there. We wanted to start a lower limit of 2 and go to an upper limit of 5. It automatically shades that area in for you and calculates the area. So really nice that your calculator can find it that quickly. Of course, if it was a non-calculator or multiple choice, they would have 3 natural log 5 minus 3 natural log 2 as the answer? Or could you see them deciding to factor it out and have this as a possible answer, right? Or could you see them deciding to use your log laws and subtracting is dividing? Or can you see them deciding to use your log laws and put it in as a cubed? Would you get it right if you would have seen this as the answer? Because if I put that 3 in as a power of 3, 5 cubed is 125, 2 cubed is 8. And this is where the multiple choice is what, like, they have the power to be, I don't know what it's like, they can be nasty. Because there's like, I got the answer, and none of the multiple choice match up. And at that moment, you don't know if you did something wrong, or if you just didn't go far enough. So, just to be careful with that, because it could have started like this and ended as the natural log of 125 over 8. And you don't have a calculator, so it's not like you can just plug it in to check, oh, this is 2.75, right? I'm really curious if my mental math was good. 2.75. Whew. Nice. So we have to be good at finding our antiderivative, which was our very first thing that we did in class. And then we just have to plug in numbers. Sometimes our antiderivatives can be tricky. Like here I have x plus 1 over x. Each of those on their own would be easy to do the integral, but I have it squared. So that squared is causing a problem. Because it would, if this was a derivative, you would have a chain rule if you had to do that derivative, right? You do the derivative of the outside function and then multiply by the derivative of the inside function. But for integration, we don't have a chain rule for integration. So the first thing you would have to do in a question like this is algebraically play around with it. Actually square it out. And if you squared it out and FOILed it out, you would get x squared plus 2 plus 1 over x squared. And now that squared on the outside is gone, and each of the things that are left, you can find the antiderivative for. Remember your power rule antiderivative? Add 1 to the exponent and divide. So the x squared is going to be x cubed over 3. The 2 is just going to be 2x. And the x to the minus 2, I would actually write it like this. I would add 1 to that exponent and divide. That's not an equal sign. I'm going to put an arrow. Because they're not equal. And I found the derivative, or I found the integral. Maybe I should actually... There we go. That's proper notation. Add 1 to the exponent, makes it a negative 1, and divide. And then the minus 1 on the bottom, I changed to a subtraction sign. The x to the minus 1, I changed it back to 1 over x. And when you have multiple things, we're now going to plug in 4 and get an answer. And then we're going to subtract plugging in 2. So it makes sense to do a big set of brackets where you plug in the 4, and a big set of brackets where you plug in the 2. And now it's just mental math. Oh, by the way, if this was on your exam, you technically could leave your answer like this and just walk away. Because all that's left is calculations. They assume you know how to do them. You assume they know how to do them. And you go, yeah, Go ahead. It feels, I don't know, as a person that does math, it would feel very wrong for me to say, here's my final answer. I'm not going to simplify it any further. I feel like on all your quizzes, I'm going to ask you to get a final answer of a fraction of 275 over 12. If you wanted to write it as a decimal. But you would get full marks on the exam if you left it any one of those with calculations to be done.
Can you go up a little bit?
I can go up a little. Is that enough?
Yeah.
And it's really nice you have your calculator because you can plug any of these in, type them into your calculator, and get the answer right away to check if you've got the right value or not. So let's say you got 275 over 12. I go to my calculator.
Hello, delivery free.
Because it was an area, and we don't have any, if it was centimeters, it would be centimeters squared. This is just units squared. So how do we know it's an area? Anytime you're finding an integral,
Oh, my bad.
it's area under a curve. So what I want to show you is that you got 200, let's say you simplified, you got 275 over 12, and now I can go to my calculator and I can type in x plus 1 over x in brackets, x plus 1 divided by x, all squared. That was our function, right? I can hit graph on that function. Wow, it looks interesting. And I can go second calculate the area from 2 to 4, and I get 22.9. Okay? What's interesting is sometimes when you calculate stuff on your calculator right here, if I go second click, I'm going to just check, and I store my last answer as x, it remembers that the last answer you did was actually on the graph. And so now I have this answer from my graph as x, and I can use it for other calculations if I wanted to, or I can go math fraction and change it back to a fraction and see that I should get 275 over 12, which is kind of exciting. It's a weird looking graph. So there's the picture of what's happening depending on the window that you're looking at. Found the area under that curve from 2 to 4. But in order to do it without a calculator, we would have needed to manipulate your integral so it's something you can do the antiderivative of. And that's where that purple sheet that we had before, this is the ones you're allowed to use so far. These are the only things we can do, only if it matches up. So the way this one was originally didn't match up with anything because it was something squared. We had to square it out to begin. Okay, can you imagine if that was instead of squared, power of 7? You would have to multiply it out 7 times in order to get it. Oh, and we've also learned that if what you have inside is the form of a line ax plus b, you can undo that chain rule. So that was another strategy that we've learned so far. Antiderivative of e to the 3x is? E to the 3x over 3. Because if you did the derivative, you'd have e to the 3x times by 3. So the integral would have to have the opposite and divide by 3. A 1 over x is a natural log. If you have a 1 over x plus 1, it would be the natural log of x plus 1. If there was a chain rule of the x plus 1, you just have to times by 1. So technically I could divide by 1, but I don't need to show it. And then we have to plug in 1 and plug in 0. Big set of brackets when I plug in the 1. Big set of brackets when I plug in 0. And now it's just a matter of simplifying. And I would like you to try the last 3 on your own. I will scroll down. Can I scroll down to here now? And show you the simplified answer. If you want to know what this looks like on the graph. So on a non-calculator, you leave your answer as e cubed over 3 minus 2 natural log of 2 minus 1/3. Well, technically, I guess you could leave it as any one of those. Here we go. Did you get the right derivative? Negative cos 3x over 3. Then plug in. And those values are on your unit circle. So you get 0 plus 0? Did you feel like something must have went wrong? If you look at what happens, there's an area above and an area below. Areas above are positive, areas below are negative. And it all cancels out. Yes?
Sometimes the calculator does that. Like, notice when I did derivatives, sometimes the derivative was when it would say like
E to the minus 14.
Yeah.
Yeah. So what's happening there, and mathematically, e to the minus 14 is scientific notation, which means you should have 0 decimal, and then move your decimal place over 14 spaces. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 7, which is so close to 0 that if you rounded, you'd be like, that's basically 0. So what's happening, and why does the calculator do this? Well, the calculator is actually doing calculations. It doesn't have the fundamental theorem of calculus built into its repertoire. Obviously, higher level things on the internet do. But this calculator is probably actually doing something along the lines of adding up little rectangles. And it can add up a lot of little rectangles quickly. And it probably has something built in that says, once the rectangles are this small, you're probably close enough you can stop. And it stopped, but it wasn't quite, we know the answer is exactly 0. So actually, in this case, what I said before, if I was betting on someone, you were right. And the calculator is off a little bit. And this is like, oh, I must be really smart. I'm smarter than my calculator in this moment. Yeah. I'll put up the answer for the second one in a second. It was a little weird from 3 to 2. But that's okay, you just work with it the same way, but you write 3 to 2. And you would, hey, this is power rule, so add 1 to the exponent and divide, and because this is an ax plus b, we'd also have to divide, because if you did the derivative, a chain rule would multiply by 2, so integrating, we have to undo that chain rule and divide by 2. Then plug things in, and you get -2/10.